Types of chemical reactions. The first part is combination and decomposition. There's several ways to classify chemical reactions, and I'm going to use this method here. It's presented in your book. Your book presents a couple of different ways, but I like this classification, and it's the one the lab manual uses, so let's work with this. So the first type is combination or synthesis, and that's when two small compounds or two elements combine to form one. You recognize it because there's only one product. And decomposition is the reverse of that. You start with one reactant and it breaks down into two or more simpler molecules, or it could be elements. So synthesis, you have one product. Decomposition, you have one reactant. We've got single replacement where you have a compound and an element, and you've got a partner switch and you end up with a different compound and element. Double displacement, you have two compounds and they switch partners, you end up with two compounds. And combustion, you react with oxygen. There's another type, oxidation, which actually several of these fit into the oxidation category. So they're often called redox reaction, oxidation reduction, and it's where elements change their charge. And so at the end, we'll talk about which one of these categories. There's actually 3 of these categories, 4 that fit into that category. Let's look at combination or synthesis. So that's when 2 or more reactants combine to form one product. So you can see that in A plus B makes AB. So you end up with one product. And you can see the little cartoon how the two people got together. An example of that is to make water out of hydrogen and oxygen. So, and that's an example of a nonmetal reacting with oxygen. Oxygen reacts with both metals and nonmetals. The next example is a metal reacting with oxygen. So you can see magnesium will react with oxygen to make magnesium oxide. And again, you can see combination. 2 things come together to form one. And it's interesting that both these reactions can also be considered combustion and redox. So the classification, sometimes it'll fit in more than one category. Decomposition is the reverse. So one compound breaks down into 2 elements. So now you see you have AB, and it breaks down to A plus B. So it's the reverse, and you can see your couple breaking up. Some examples, HGO breaks down to HG and O. So you've got a compound breaking into its elements. So that can happen. Metal hydrogen carbonates and metal carbonates can break down. So you have sodium hydrogen carbonate breaks down to sodium carbonate and water and carbon dioxide. And carbonates can also break down. You've got calcium carbonate can break into, copper carbonate breaks into copper and carbon dioxide. This one is pretty interesting because this is the reaction of baking soda. Sodium hydrogen carbonate is baking soda, and when you heat baking soda, it decomposes. And one of the products is carbon dioxide gas, and so that's how it works in baking. The carbon dioxide puts little gas bubbles in whatever you're making and makes them more fluffy. Often decomposition reactions require heat, and that's what this arrow with the triangle over it, it means with heat. So that's how decomposition often occurs. Part 3, single replacement. Single replacement is the next one. And so single replacement is where reactants are an element in a compound and the metal switches places. Now it could also be the non-metal, but the ones we're going to consider, it's the metal that switches places. So you can see that you have A, so we have a metal by itself, plus BC, a metal in a compound. And what happens is the A and B switch places so that A is now in the compound and B is by itself. So that's how a single replacement reaction works. And we determine these based on the activity series. And on your periodic table, you have this activity series, and it lists the metal from the most active to the least active. And the most active metal is the one that would most want to be in a compound. So lithium really wants to be in a compound, where gold, not so much. And so in any single replacement, you can decide whether that's going to happen or not based on the activity series. So let me show you how that works. So if you consider this is single replacement. We have copper, that's an element, and silver nitrate, that's your compound. So you find those two metals in the list. So here's the silver, and here's the copper. So the one that's higher is the copper. That means copper wants to be in the compound. You look at it, it's not. Copper is all by itself. Well, it's not happy that way. The higher one wants to be in the compound. So the two metals are going to switch places. So the copper is going to go with the nitrate. So that here's the nitrate. And the silver is going to be by itself. Now you may wonder, what's that 2 doing? AgNO3 2. And that has to do with the charge. So silver has a positive charge. And copper has more than one possible charge. So you kind of have to know what charge it's going to be. But in this compound, it's +2. And since it's +2 and nitrate is -1, it needs that 2 to balance the charge to make a neutral compound. And that's why the 2 in front of the Ag happens as well. Okay, so that's how you see that working. Let's look at the next example. We have iron and copper. So if we find those, we already found copper, it's right here, and iron is up here. So you consider which one is higher. Well, the iron is higher, so it's the one that wants to be in a compound. And over here you see iron's by itself, so they got to switch places. So now the iron goes with the sulfate. All right, and again we balance the charges. The copper here was +2. The iron is also +2. Okay, so that's how you come up with FeSO4. Remember the SO4 is -2, and then the copper is all by itself. So single replacement, the metals switch places. The next one's a little bit different because we have magnesium and then we have an acid, hydrochloric acid. You think, well, is there a metal there? There's not really a metal, but hydrogen in an acid kind of acts like a metal. It's a cation. And so the magnesium and the hydrogen are the things we're going to look for. So here's hydrogen. It's in parentheses because it's not really a metal. And then the magnesium is clear up here. Well, magnesium is higher, so it'll want to be in the compound. So you see we put the magnesium with the chloride. And again, magnesium's +2, chloride's -1, and that's where that 2 comes from. So that's one of our products. And then we put hydrogen by itself. But hydrogen by itself is not like the copper that's a solid. Hydrogen by itself is a diatomic gas. So that's H2 gas, and that's where we get that product. And then once we make those compounds, then we balance it. And we can see we have 2 hydrogens, 2 chlorines, and so that's why we have this 2 here. All right, let's look at the last one. The metals we have are copper and silver. Now we've already looked at copper and silver. Here they are, copper and silver. And the one that's higher is copper, which means copper should be in the compound. Well, it is. See, copper is in the compound. So it's already happy, nothing's going to happen. And that's why we put NR, no reaction. It's happy the way it is, it's not going to switch. Let's look at hydrogen in a little more detail. Because hydrogen is on this list, hydrogen as an acid, the metals above hydrogen will all dissolve in acid. So you see hydrogen clear down here on the list. All the metals above it dissolve in acid. So for example, and this is one that you do in the lab, if you put zinc in hydrochloric acid, well, zinc is right here, and it's above H. So zinc doesn't want to be the metal, it wants to be in the compound. So when we look at zinc and HCl, what's going to happen is the zinc and the HCl will switch places. So now the zinc is with the chloride, and the 2 comes because zinc is +2, and the hydrogen is by itself. And remember, that's going to be H2 gas. And so in effect, the zinc dissolves because the zinc chloride is aqueous, and the hydrogen becomes a gas. So what do you see? What is the evidence? You see bubbles, the hydrogen gas forming off of that metal, and the metal is dissolving. Now the top 6 metals are bolded, and these 6 will treat water like an acid. So they are strong enough or active enough metals that they'll pull the hydrogen out of water. So here's an example of how that works. So calcium is one of these metals, and this reaction on the side is calcium in water. And what happens is that the calcium, if you think of water as HOH instead of H2O, so one of these hydrogens is going to switch places with the calcium. So it becomes calcium hydroxide. Okay, so that calcium is +2, hydroxide's -1, and that's why you get the 2. Calcium hydroxide, and then this hydrogen is going to be elemental, which is hydrogen gas. And then since you have two hydrogens, you need 2 waters to make it balance. So the top 6 metals will do that. Not all the metals above hydrogen will dissolve in water, but the top 6 will. And you might remember the cesium in water reaction that was so violent. That's an example of this type of reaction. Part 4, double replacement. Double replacement, both the reactants are ionic compounds. So they have to be soluble ionic compounds. So that's what your reactants are, and they switch partners. So here you have A plus B, C plus D. They're going to switch so that the A goes with the D, the C goes with the B. And so they totally switch partners. In these, they're always aqueous. And the reason the reactants have to be aqueous is if they're not dissolved in water, the partners aren't freed up to switch. So when an ionic compound dissolves in water, the ions split apart and they're free to look for new partners. And so that's why they start out aqueous and then they can switch. So I left the products blank because I want to show you how you figure that out. Okay, so if you think about it, switching partners in this first reaction, silver is plus. That's your positive. So if it's going to leave the nitrate, would it go with the sodium that's plus or the chloride that's minus? Well, it only makes sense for it to go with the negative. The positive goes with the negative. So silver is going to go with the chloride. And so we're going to have Ag and Cl is one of our products. Now when we put it together, we have to balance the charge. So silver is plus, chloride is minus. We're good. We don't need subscripts. So that's one of our products. The next product, we're going to take the sodium, our other positive, and put it with either the silver that's plus or the nitrate that's minus. Well, the only thing that makes sense is put it with the minus. So we're going to put the Na with the NO3. Okay? And again, sodium is plus, nitrate is minus, and so we don't need subscripts. It's good the way it is. So that's how we switch the partners. And another way to think about it, if you remember FOIL from math, it's the outer and the inner. It's just the middle part. That the outer 2 are going together, the inner 2 are going together. And that's how you make your new compounds. And you always have to balance the charges. So that's the first step, is to switch the partners and balance the charges. Now, having those charges is not appropriate in a reaction. So I'm going to erase them once I'm done and have no charge on it, because that's the point of the subscripts. The next thing, the way we know if there's a reaction or not, is based on the solubility rules. And these are also on your periodic table. So let's take a minute and look at these solubility rules. So the first column, and I write AQ on that, these are the ones that are soluble. So generally soluble: lithium, sodium, potassium, ammonium. If you have those in a compound, it's going to be soluble. Now that's the only rule we have with cations. The rest of them are about the anions. So those cations are always soluble. We have two anions that are always soluble: acetate and nitrate. So rule 1, 2, 3, if any of those apply, it's soluble. The rest of the rules include some exceptions. So halides, that would be chloride, bromide, iodide. They just call it X as a general for the halide. They are soluble except for these three. Silver, mercury, and lead are not soluble. All the rest of the chlorides, bromides, iodides are soluble. Sulfate is another example where most of them are soluble. The exception: strontium sulfate, barium sulfate, lead sulfate are insoluble. All the rest are soluble. So that's our aqueous side. The next side are the ones that are insoluble, or they'll be the solid. So carbonates are generally not soluble. They'll generally be a solid, except for rule 1. If you have lithium, sodium, potassium, ammonium, it's soluble. That is also true with chromate and phosphate. It's only rule 1 that is soluble. All the rest are insoluble. And then when you get to sulfide and hydroxide, they have the rule 1 exceptions, but they also have 3 more. Calcium, strontium, and barium as well are also insoluble. So these are the rules. You don't have to memorize them. They're on your periodic table. You'll always have them to look at. But when you do a double replacement reaction, the next step is to look at your two products and figure out if they are soluble or insoluble. So let's do that with the reaction we just did. So silver chloride. The rule, we're going to look for the chloride. And notice silver chloride is one of the exceptions. So this is solid. It's in the aqueous side, but it's an exception, so it's solid. And then sodium nitrate, well, that's rule 1 and rule 3. Those are always soluble, so this piece is aqueous. And so we do have a reaction because we made a solid. If these had both been aqueous, we would have no reaction. So that's how it works. And since we have a reaction, now we should balance it. And so we look at 1 silver, 1 silver, 1 nitrate, 1 nitrate, 1 sodium, 1 sodium, 1 chloride, 1 chloride. So it's balanced. And that's how we approach double replacement. So let's look at another example. And if you'd like to pause it here and try this next example on your own, that's a good idea. So what we're looking at in this one, we're going to put the K with the NO3. So we put K and NO3. We also have to consider the charge. K is plus, NO3 is minus. So we're good. We don't need any subscripts there. All right, so that's one of our products. The other, we're going to put the lead with the iodide. So we put Pb with I. And look at their charges. Now you may think, well, we don't know lead's charge. It could have more than one possible charge. But whatever its charge is, it keeps the same charge. These are not redox. So we look over here, the lead is with 2 nitrates. So the lead has to be plus 2 in this case. So the lead is plus 2. And the I, well, I is minus 1. So that's not balanced. And so in order to make that a neutral compound, we need 2 on the I, PbI2. So that's our first step, is to identify our products. And now I'm going to erase those charges because we don't want them hanging around in our balanced reaction. And now let's look at solubility. So solubility, the first compound, it has a K in it. There's rule 1. Potassium is always soluble. Also nitrate, always soluble. So this piece is aqueous. And then the PbI2, well, that's rule 4. I is usually soluble, but Pb, that's our exception. So this piece is solid. So we do have a precipitate, and that's what you'd see in these reactions. You'd see a solid forming. It will get cloudy. And so let's go ahead and balance it. There's already a 2 in front of Ki, sorry, but imagine there wasn't. The reason we need that is we have 2 iodines, so we need 2 there. That gives us 2 potassiums. And then we have 2 nitrates and 1 lead, so that's balanced. Here's those same examples, just written out a little more cleanly so you can see those balanced reactions. Neutralization reactions are another kind of double replacement. So what we were looking at are precipitate double replacements. They make a solid. Another thing that can happen is that you make water. So instead of precipitate, we're going to make water. And another way to think of it is you have an acid and a base. So an acid is a compound that produces H+ ions, hydrogen ions. A base is a compound that produces hydroxide ions. And if you can imagine, if H and OH get together, well, that's water. That's H2O. And so that's a new compound, but it's not a precipitate. So look at this example. So we have HCl and NaOH. Well, this is our acid. Okay, and this is our base. So we have an acid and a base. It's going to work just like double replacement. The H is going to go with the OH, forming HOH or H2O, water. And then the Na is going with the Cl to make NaCl. And the same rules apply. We balance the charges, and then we balance the reaction. And this is also a chemical reaction. You don't see a precipitate. You actually don't see anything at all. So we often use indicators so that you can see a neutralization reaction happening. But forming water is a new compound. The product, acids and bases, your reactants, are very dangerous solutions. And the product is water and salt. So something you could actually drink. You wouldn't want to drink a lot of it. But you've really changed the properties of the solution completely. And so that is definitely a chemical reaction. Let's try this next example here. We have HBr, SrOH. So hydrobromic acid and strontium hydroxide. So the H is going with the OH, and that makes water, H2O. Or you could write it HOH. You can write it either way. And the Sr is going with the Br. So plus Sr, Br. Now, I didn't show the charges. H is plus, OH is minus, so we just need one of each. Strontium is +2, bromide is -1. So in order to make that balance, we got to do SrBr2. And those are our products, and now we need to balance it. The states, we'd put liquid for water, liquid, and this one, check your solubility rules. Usually the salt is aqueous. So in our last example, the salt was NaCl, which naturally you would call that salt. But salt is actually a broader term, and any ionic compound that's not an acid or a base is considered a salt. So the strontium bromide in this case is the salt. Let's also balance it. what I notice is I have 2 BRs, but only 1 BR here. So I'm going to put a 2 in front of the HBr. And the SR balances, so let's check the hydrogens. I have 2 plus 2, so that's 4. So I'm going to need 2 waters. And then the oxygens, I've got 2 oxygens and 2 oxygens. So that's balanced. And of course, I'd erase. Let's go ahead and do that. You don't want to leave the 2. You don't want to put the arrows. And that's a little bit more clean. Part 5, Combustion and Redox. Combustion is another kind of reaction, and that means reacting with oxygen. Reaction of a substance with O2 to form one or more oxygen-containing compounds, often including water. That's what a combustion reaction is. They're usually exothermic, they release heat, and compounds containing carbon and hydrogen, or carbon, hydrogen, and oxygen, always form carbon dioxide and water when you burn them. And so burning, combustion mean the same thing. So here's an example that you can see right here, C2H6. That is a hydrocarbon. It contains carbon and hydrogen. You react it with the oxygen, you get carbon dioxide, and water is the product. And this isn't the only combustion reaction, but this is super important because burning hydrocarbons or fossil fuels supplies about 80% of the energy in the U.S. This includes coal and oil to produce electricity, gasoline for our cars, natural gas, propane to heat and cook, and more. So it's a really important reaction in producing energy. So we use the heat emitted by this reaction. I'm going to say plus heat here, because it releases a lot of heat. And you all know that because you've burned stuff and you know it gives off heat. That heat can be used to heat up steam, which the pressure of the steam can create electricity by turning a turbine and moving a magnet. And so that process produces electricity. Or the pressure that builds up in the pistons of your car creates the motion of your car. So we use this reaction to take that heat energy and convert it to other forms of energy that we use in our society. So some of the downsides is that carbon dioxide is called a greenhouse gas. And so it may contribute to heating up the planet or changing the climate. So carbon dioxide and water actually, what they do is they let the heat from the sun in, but the heat that radiates back out is at a longer wavelength, if you remember that spectrum of the energies, and the heat that comes off, it holds it in. And so it acts like a blanket holding in the sun's heat, which is important. I mean, we need that heat so that we don't freeze at night. But if we increase that, we may change the climate in our planet. And so that's a concern. The other thing is, besides the greenhouse gases, that these fossil fuels often come with other elements like sulfur that produce acid rain and other types of pollution, the particulates that form. And so it's not the cleanest way of producing energy. So there's some downsides to it, but we use it a lot. And so it's important to understand this reaction and what's going on. Let's look at another one. Here's an example, C6H12O6 plus oxygen. Now we know what the products are, because always it's going to be, we start with a hydrocarbon, it's going to be carbon dioxide and water. So CO2 plus H2O. Those are our products. Okay? And so let's balance this as well. All right, we have 6 carbons and 1 over here, so let's put a 6 in front of that. We have 12 hydrogens and 2 here, so let's put a 6 in front of this. And now let's count up our oxygens. Over here we have 6 times 2, that's 12, plus 6 more, we have 18 oxygens on this side. Over here, we have 6 right here with this molecule, and so that leaves that we'd need 12 here. So in order to make that balance, we need a 6 to make that balance. And now that reaction is balanced. So there you see it written out, typed. This reaction is the combustion of sugar. So C6H12O6 is glucose. This reaction goes on in your body and fuels your body. Oxidation reduction or redox reactions are where elements change charge. Reactions where electrons are transferred. So you can think of the electrons moving from one element to another. And a lot of the categories, most of the single replacement and decomposition are also redox, and combustion and single replacement are also redox reactions. So a whole bunch of the reaction types fall into this category. And batteries use the redox reaction. So every battery has a redox reaction, and what it's doing is capturing the electrons and using that movement of electrons. Movement of electrons is electricity, and so that's what's going on in batteries. So let's just look at an example. There's no test questions on redox, but it comes up, and especially if you're studying health, redox reactions are important in biological systems. So let's look a little bit at how this works. So when you have an element by itself, it has no charge. And so that's why we give it a charge or an oxidation number of 0. So magnesium starts out as 0. And we're going to react it with HCl. And oxidation number is very often just the charge. So the H is plus, the Cl is minus. Then on the product side, now magnesium is with the chloride. So magnesium is now plus 2, chloride is still minus 1, and the hydrogen now is by itself, so it has a charge of 0. And so you can see what's changed is the magnesium went from 0 to plus 2, and the hydrogen went from plus 1 down to 0. So one went up, magnesium went up in charge, it was oxidized, hydrogen went down, and it was reduced. And it always has to happen together. The electrons flow from one thing to another. And so that's an oxidation reduction where you have a change of charge. Single replacement is always a redox reaction.